Let's do it. Okay, so today we're going to be going a little bit further into this idea of polynomials and roots and graphs and all that kind of stuff. So yeah, so let's just see what happens. So let's try to find some polynomials. And we're going to shift gears in just a little bit. I just want to make sure you guys are okay with this first phase of this. So here's what we're going to do is we're going to say given A, that it has roots at x equals 3, x equals -5, and x equals 2. And I'm going to put multiplicity 2. So what I'd like to do is see if we could go through that process, and we've already done that. But what I do want to do is make it just a smidgen harder. And so if we had some function that has those roots, guys, what would the first thing be? It would be x minus 3. And then what would be my next piece of my puzzle? X plus 5. And last but not least, x minus 2 squared. Now, this is a polynomial that has that, because keep in mind, what would happen if I put a number in front? Would it still be true? Okay, so I'm just going to basically write the simplest one, because understand I can go through and I can add a multiplier and it's not going to change what this is, right? So the tougher part comes in when somebody says, hey, I want standard form. This is a little harder. Now, when we say standard form, if you go back in time, that was actually one of the first things we did. Standard form was something that looked like this. What do you notice that is missing there? All those dang little factors. Now, the reality is, this is a beautiful form. Isn't that the easiest way to do it? That's the best way to do it. We love that kind of form if we can. It's really, really nice. Are you here for you're taking your thing? Okay. So it's right here. You can sit right up front and go for it. So let's see if we can multiply that out. So can you guys help me? Like, what would happen if you distributed this x minus 3 times x plus 5? X squared, that would be a plus 2x and a minus 15. Are you guys okay with that? Now, I have a lot of people historically that screw this one up. When you take x minus 2 times x minus 2, a lot of people get this portion correct, but they miss one little piece, okay? You can use that chair right there. That way I'm not going to bug you. What's going to happen right in the middle, though? See if you can remember the missing little piece in the middle. It should be minus 4x. You got it. Now, again, looking for standard form, I will say, honestly, this is a place where a lot of people are going to struggle, because I got 3 pieces there. This is a trinomial. That's a trinomial. So if you took a triple times a triple, how many terms will there be? That's 9. Is there a lot of room to make a little bit of a mistake in that thing? And yet, somehow, we have to be accurate and not miss any one of the 9. So there's a couple of ways that people will tell you to do that. They will say, let's distribute this x squared by all 3. And then let's multiply this 2x by all 3, and then the 15 by all 3, and then what's the last step? Add them all together. Combine those like terms. I personally don't do that. I hate that. I look at this, what's the biggest power I could get is x to the 4th, isn't it? So let's get it. What is x squared times x squared? That's x to the 4th. Okay, what would be the next highest power? Is an x to the 3rd, and I have one of them right there. You see it? That'd be negative 4x to the 3rd. What's right there? 2x to the 3rd. If I have a negative 4 and a positive 2, do you see how I have negative 2x to the 3rd? So we're far enough in math that I think we can hold on to a couple of concepts at a time. What would be the next highest power? Squared. I got one of them there. There's 4x squared. What's this one? That'd be negative 8x squared and negative 15. So what would 4, negative 8, and negative 15 make? 4, negative 8, and negative 15. That would make a total of negative 19 of those, right? Now, yeah, you have to keep a little track of a little bit this way. What's the next highest term? Just the x, which would be 8x is there, and 60x is there. What's that? 8 and 60. 68x's, and last but not least, the constant, which would come from a negative 15 times 4, which is negative 60. What do you guys think? Can you guys handle that? Now, can you imagine making a mistake? Of course you can. So on a test, if you are smart, then you graph this one as y2 and you graph this one as y1, and what better happen? They better match. I would expect and hope that you would do that, because why wouldn't you double check to make sure you didn't miss something? And if you were wrong here, sometimes I'll put this one in as y3 and make sure that I didn't somehow write that piece down wrong, because all three of these should be identical, right? So let's see if you guys can do one of these on your own. So here's B. You're going to have roots of x equals negative 1 and x equals 3/5. And the negative 1 part has a multiplicity 2. So I made yours a little bit nicer than mine because yours is a cubic. I made mine a quartic. Jolene, tell me something. There's an x plus 1, and that is true. Okay. Masra, what's something else? X minus what? 3/5. And I actually agree with you on that one, but there's an easier way. Did somebody say that a slightly different way? I would agree that you could say x minus 3/5. Ah, almost. It's 5x minus 3. Yeah, that's a little bit weird how that works. So when you see that fraction, yeah, you could do that and it's not wrong. And in fact, if you did that, your problem will work. You're just going to have harder coefficients to deal with. Did anybody notice there's one thing that you guys forgot? Where does the square go? Okay, now, I would say really, really cautious about that. Who can square this x plus 1? Because this is a place, this is called the binomial distribution. That sounds scary, doesn't it? Binomial distribution. You know why it's called that? Because that's a binomial. And what you have to do is you have to take x plus 1 times x plus 1 and you have to distribute it. Woo! It isn't that big of a deal. So who can do that? X squared plus what? 2x and a 1. Okay. Now, again, I'm going to go my styles. So what's the biggest one that we could get? Biggest exponent there. Third. How many thirds do we have is 5. 5x to the third. Okay. Now, x squareds. How many x squareds do I have? As I have, it looks like negative 3x squared, and how much else? A 10. A negative 3 and a 10 makes 7 of those. Now I'm going to shoot for my x's, and I've got negative 6x's, and I've got 5x's. That's negative 1x. And what's my last constant? Negative 3. Now, if you really want to do the full distribution and write all 6 terms and combine your like terms, it really doesn't take a lot more time. I'm just a little bit lazier. So I just go at it that way. Now, the last one, and then I'm going to shift gears and do something that is going to seem very, very different to you, is what if someone is mean and says, oh, man, is it possible that you have roots that are not nice? Did you do that in algebra 2? Sometimes have roots that are like 5 minus root 3. Dang it. But usually you got these roots when you did the quadratic formula, didn't you? And if that root was sitting there, this is a really, really important thing to note. I gave you part of the information, but I didn't give you the whole story. If 2 plus 2 roots of 3 is a root, then guess what? So is 2 minus 2 roots of 3. That's called the conjugate roots theorem. If you have one of them, you always get its partner on the other side of the aisle. So that's kind of weird. So you're not going to like this, but I'm going to just take you through the story. So notice when you said I had a root at minus 1, what did you write in here? Is you wrote x plus 1. When we had a minus 5, you did a plus 5. Cool? So here we go. Hold on to your hats, everybody. This one's a little harder. So I'm going to have x minus 2 roots of 3, and I'm going to have x minus 2 plus 2 roots of 3, and I'm going to have 3x plus 2, and I'm going to put an a in front. Here's h of x. Now, that is going to look kind of nasty, I understand. So I'm going to ignore this guy right here entirely for a moment because I'm going to tangle with the big boss right here. And this time and this time only, I'm going to do this the real way because I think with all those roots, there's room for mistakes, right? So if I distribute x, I'd get x squared minus 2x and plus 2 roots of 3x. So notice that I went through and I distributed that x by all 3. Now what am I going to distribute? The negative 2. Let's distribute that negative 2 through. And that's going to give me a negative 2x, a positive 4, and a minus 4 roots of 3. And then we have one more thing to distribute. Oh, I don't like that color. Maybe this is going to work. And then I'm going to distribute this one right here. I don't know. Does that look a little different? My orange disappeared on me. I was trying to make sure that I had everything a little bit different. So my last distribution is negative 2 roots of 3x plus 4 roots of 3. And ooh, what is 2 times 2? 4. And root 3 times root 3 is 3. And 4 times 3 is 12. So 2 roots of 3 times 2 roots of 3 is 12. Okay. Woo! That's a lot of stuff. That sucks. But there's a confirmation coming if we did it right. Look what happened. Study it. Do you see anything good? Anything convenient? The positive 2 roots of 3x and the negative 2 roots of 3x cancel. Do you see anything else that is convenient? The 4 roots of 3 and the 4 roots of 3 cancel. In other words, all of those pieces that were gross and ugly, what happened? They canceled out anyway, didn't they? So when we put it all together, let's see. I had my x squared here, that's it. I had a negative 2x and a negative 2x for a total of negative 4x. And then if I go all the way down, there was a 4 and a minus 12 for a total of minus 8. And boy, I didn't need that much room. So I'm going to go ahead and make that parentheses go away. And then we just had 3x plus 2, right? Does that seem so bad? Now, it was a little obnoxious to get there, but what happens if you do those problems is something exactly like this. Now, boy, I hope I don't run myself out of time because I'm still kind of working. So let's just go ahead and take a look at something. X squared minus 4x minus 8. And no, I'm not done, but I'm getting close. See, the thing I'm worried about, everybody, is could I have made a mistake in here? I'm sorry, you kind of can't see that. Let me go back up a little bit and hold my calculator right here. And I'm going to hit a zoom 6. Now, I should see a little cubic, and it should have 3 roots. Do you see all 3 roots now? So watch this. And this is a new button that I haven't really shown you much with yet. But it's if you go to second calculate, the first one is the number value, right? And I just hit value. And I want to ask a question. What happened in theory at negative 2/3 if I have done this correctly? What should be the value at negative 2/3? It should be 0. Did my cursor actually hit perfectly there? Now also, if I tried the value 2 plus 2 root 3, and a cool thing is the way your calculator's set up is as soon as you say value, you can just keep hitting enter, 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 and it'll keep giving you new values. So what should 2 plus 2 roots of 3 be? Should be the same thing. It should give me 0. So do you think I did okay? I can do one more, 2 minus 2 roots of 3. And I can see that right now, what I have written, is it worth continuing my process? Because I have good answers. It was worth a little teeny bit of effort, so let's go one step further. I've got 3x cubes. How many x squareds do we have? So I got 2 there and negative 12 there for a total of 2 there, negative 12 there, looks like negative 10. I got some x's, I got negative 8 there and negative 24. My goodness, negative 8 and negative 24 is negative 32. That was x's, not x squareds, excuse me. And then minus 16. And this is what I've got. Oh, I missed one little piece of the question that was very, very early. It says, wait a minute, my leading coefficient was supposed to be 6. What does that make A then? What would the leading coefficient have to be to make that actually true? What number times 3 would give me that 6 that I'm looking for? 2. So if I made A equal to 2, would that actually fix it? So what did I do to all of those values? I distributed A 2 because that 2 made the leading coefficient 6. And guys, what would happen if I graphed this thing? What do you think would happen? It has the right coefficient. Could I check the roots and make sure they were all there? That's my story. That dials it in. So I kind of laid this out. So here's the deal. Do you guys like better? Which form do you like better to work on? Do you like this form better? Or do you like that form better? Do you like factored form or do you like standard form? Isn't factored form way more bueno? Isn't that like a way superior way to look? Like you can understand what's happening and all that kind of stuff. But the reality is in the real world, rarely do you ever say, here's a problem in factored form. You just do some work and it's like this big ugly beast shows up. And what is your job then is to say, can you start here and get to there? Because this is hard to understand. This is very doable, isn't it? So that's what we're going to be working on for the next couple of weeks. How do you take something that looks really bad and make it look more understandable? Okay, so what do you call something when you start from here and you try to get to here? It's called factoring. You're taking this and you're breaking it like a factor tree into all of its little component parts. It's factoring. Well, wait a minute. What did we do to go from here to here? You tell me. We distributed, but isn't that a fancy word for multiplying? So if this is multiplying, what are we doing this way? Aren't we dividing? Aren't we taking something that has been multiplied out and dividing it into its component little parts? Well, ladies and gentlemen, here we get to have our fun. We have a visitor.
Yes, you do. I need to come meeting with the parent. No, obviously it doesn't or anything, but I need Stephanie, Jolene.
Yep.
Daniel.
Yep.
Ashley. I'm reading my notes. I thought there were 4. No, I just need 4 out here. Those 4. So,
How long are you guys going to be gone for? Okay, good to know. Okay, so watch, if you don't make it back, just watch the video. You'll see the end part. You can fast forward to that piece. Okay, all right.
I have an opportunity for yeah.
All right, awesome, cool. All right, so here's what we're doing. We have just gone through the process of multiplying it out. But the problem is that's really not what I wanted to do today. I wanted to talk to you guys about how you go the other direction. And I'm just warning in advance, this is the part that people find to be pretty uncomfortable. Do you guys remember long division back in 4th grade? Welcome back. Sorry, everybody. It's a bad thing. But see, multiplying people are pretty good at. Dividing is a little bit harder. So what I'm going to do is, and again, just bear with me. This is kind of a dorky thing to do, but just kind of follow what happens. So I'm going to take you back in time, back to your days that are earlier. And let's say someone says, I want to take 7 and divide it into 852. You guys remember doing that? Don't you wish you could do that again? Like that was as hard as math got. You're like, woo, I could do that. I could ace that test. So what would you guys do first? So let's remember the process, because again, what I'm going to show you today in more advanced techniques is this. So I want to be really clear. So what's the first thing you decided back in the day? Is you would say, well, what number can I put right here so that when I multiply it by 7, I get as close as possible to this first piece? What would it be? It would be 1. So then we multiplied and you got that. Now, the next step, you're like, well, duh. But what did you do? You didn't leave it as a 7. What did you do? You made it a -7. In other words, you took that +7 and you made it a -7. Then what did you do? You dropped everything down. And a lot of times people drop the whole thing down, but some of your teachers just told you to drop down as much as you needed, because I'm not going to get to that 2, am I? So now what? You go to the same thing. You go to 2, and then you go 14. You're like, oh yeah, better make that negative again. And then we drop this down, and this will be a blast from the past for you guys. Now, again, I'm not trying to like talk down to anybody, like going over division from 3rd, 4th grade, but you understand what I'm after here. 7. And then what, do you guys remember what you guys did with this last little piece right here? Yeah, a remainder. Yeah, we'd write R5. Did you guys like R5? Now, when you got a little bit older, what your teacher would have told you is that, oh, well, that means 852 divided by 7 is 121 5/7. Because that's what that is, isn't it? I got 121 of them, but I got 5 extras over here, so that's 5/7. So, ladies and gentlemen, that's what we're going to be doing, but with polynomials. So, here's what we are going to do. If you took f of x and divide it by d of x, what you're going to get is some new function h, and you're going to get some remainder function over that original divisor. Now, what did you hope happened back when you were in elementary school when you did this? What were you hoping r was going to be? Oh, and you know what? If we're going to factor, what do you want the remainder to be? I want it to be 0. So if somebody says, hey, factor the number 84, you're not going to pick 11, are you? What number would you pick for 84? You'd pick 2 because its remainder r would be 0. And then you'd pick 2 again. And then you'd pick 7. And you pick all these nice numbers that are going to go in perfectly. You guys cool with that? So we're going to hope to find those. So here's my little example. X minus 3 dividing into 2x cubed minus 4x squared. Did you guys do this in Algebra 2? I think you did. Well, and this is one of those cases, I just don't know. Some Algebra 2 teachers do this more than others. But do you think this number will divide perfectly into this? Anybody have a guess? I'm going to say I don't think so. Because there's no way that 3 being multiplied by something is going to give me a 2. In the same way I said 84, you wouldn't divide by 11 because you kind of look forward and you know that 11 is not going to work. 3 times something is not going to be, it ain't going to happen. So, okay, so what do I need to multiply to get as close as possible to 2x cubed? So here comes, this is the fun part. What do we want to multiply by to get as close to 2x cubed as possible? 2x squared. Does that make sense? What would 2x squared times x be? 2x cubed. So the only thing is I'm going to say, unlike up here where you tried to get close, we're not going to get close. We're going to get perfect every single time. So what was the next part of your algorithm? Once you figured out what you wanted to divide by, is you multiply, didn't you? And I got 2x cubed and a minus 6x squared. Okay, now what? What was the next part of the algorithm? After you multiplied, what did you do? You made it negative. Well, you know what happens when you make this negative is you actually made that one negative and that one positive. Because you subtracted a negative, didn't you? Now, what did you do in our algorithm after we subtracted? You just add down. So now I'm going to get a 2x squared and an 8x. Now I could drop that negative 2 as well, but I don't think I'm going to touch that on this next step. So what do we need up here so that I could get a 2x squared? What times x would be 2x squared? 2x. Now, do you guys notice a little structurally how I put x squared on top of x squared and I put x on top of x? That's kind of the protocol we always do, because once I get to here, anything else is going to be my r, isn't it? When I run out of places to write it, that's a hint that I'm into remainderville. So 2x times x is 2x squared. 2x times negative 3 is negative 6x. So now what? We're going to change my signs and add down. Now, the reason I say change the sign is when you subtract, doesn't subtraction change positives to negative and negatives to positives? So instead of saying subtract, I just say change and add. What do we need here? I need 14, don't I? Okay, I need 14. 14x minus, I think that's 52. Change my signs and adds, and I'm out of room. I don't have anywhere left to write. What does that mean? It's my remainder. What was my remainder? Did I make that? This was 42. Thank you. So what was my remainder? 40. Or 40. I got a remainder of 40. Isn't that cool? Woo! Hey, my goal was to factor this thing. So was x minus 3 a factor? Did it go in perfectly? Oh, I failed. Okay, so let's try x minus 2, see if x minus 2 is a factor. Would that be an intelligent thing? Should I just start throwing spaghetti at the wall and hoping that I find something? You see how long that would take me? How many things could possibly go into this thing? It's an infinite number of options. Would this be smart to just randomly start dividing? So what happened, guys, is back in the day, there was these mathematicians that they went through all of this, but they're like, that's dumb. I want to narrow my search. See if I can come up with a list of ways to look at this thing and figure out what my options are that are worth the effort. Now, Descartes is one of the main players in this in the early stages of it. Descartes would have never, ever tried x minus 3. The reason why? It ends in a 2. So you know what he would have tried? What goes into 2? 2 and 1. So he would have tried x minus 1, x minus 2, x plus 1, x plus 2. Those are the ones he would have tried. Or maybe a half. I'm giving you some foreshadowing. There's a little bit of stuff that's going to happen in there too. But he would have never tried that. So what we're going to try to do is, I want you to understand, is this painful a little bit? So before we deal with the pain, we want to make sure that it was even worth doing the pain first. I have one last one that I want to see if we can do together, and I'm going to skip my extra ugly one. I had a really nice one for you, but I won't. Find the quotient. Now, by the way, the quotient is the answer to a problem involving division of, you're going to get 2x to the 4th plus x cubed minus 3. Now, there's something there that is, do you notice anything that I did? I got x to the 4th, I got x cubed, and I go minus 3. I missed the x squared and I missed the x. So if I said, hey, I got 1,005, you don't just write this down, do you? That's not 1,005. What do? We put some placeholders in there, zeros, right? So guys, when you do your problem, I'm sorry, you can't see that. When you do your problems in your division, just like you would not write 1,005, you're going to put a 0x squared in and a 0x in, because you want those placeholders so it lines up well. And you're going to find the quotient of this and, sorry about that, and this. I think I picked x squared plus x plus 1. So I'm going to help you set it up, and then I want to see if you guys can start doing this. Now, I started it. I didn't finish it. Let's see if we can find out what that quotient is. Oh yeah, it's all there. I just started it. How many x squareds are there? There aren't any. And then there aren't any x's, and then there's the minus 3 at the end. So you want all of that. So those little values at the end are kind of significant. And make sure you started that right. Did you guys all start with 2x squared? Because 2x squared times x squared would be 2x to the fourth. Pause a moment. Kind of did the next little piece for you, making sure that you don't replicate bad math. You guys got the next piece, anybody? Minus x. I like it. It's going to be a minus x cubed, a minus x squared, and a minus x. And then what? Change. That's going to be a minus x squared, a plus x, and a minus 3. A lot of room for error in these. These are hard. We will not do a lot of this. I will show you a faster trick that is a beautiful trick. Soon. I think some of you know the trick too. Do you guys remember synthetic division from last year? I bet you do. When you see it, you're going to go, oh yeah, that, I like that. That stuff was easy. You're going to see it. We'll do it soon. What's the last piece? What's the last piece to get into negative x squared? What do I need so that I get negative x squared? What would I multiply by x squared to get negative x squared? A negative 1. A negative 1, which is going to be negative x squared. It's going to be a negative x. It's going to be a negative 1. And I go in, I change all my signs. And I got 2x minus 2. So should I keep going? Why don't I keep going? I got no room left. And also, if I multiply by x squared, I can't get x. That doesn't make sense. It's going to go the wrong way. So I'm going to write it the other way. So we could write it as an r, but I'm going to write it this way instead, like you did when you were a little bit older and you'd write that remainder as a fraction. You guys okay so far? Now, is that comfortable, happy stuff? Yeah, not maybe so much, but wanted to show you something that's really stinking cool. I'm going to go back to this, and I don't know if you guys actually gave yourself enough room on that first example to do this, but this is really kind of neat. You see this guy right here, x minus 3? This is a really important one, so pay real close attention to this, everybody. You got number 3 right there? That x minus 3. The root of x minus 3 would be 3. Okay? So what I want to do is I want to take a look at this function right here. Call f of x 2x cubed minus 4x squared plus 8x minus 2. And I want to try something. Can you guys find f of 3 real quick? Now, f of 3 literally means just take 3 and plug it into the function, doesn't it? And yeah, if you need to use a calculator, that's perfectly legit. I got 54 from the front chunk. What'd you get on the second one? And then a 24 and a minus 2. And it just looks like a bunch of stuff, doesn't it? Nothing magical yet. What do you get when you put it all together? What was it? 40. Is that a coincidence? Is that a coincidence? It's not. So guys, here's the cool thing. This is pretty neat. If you ever plug the number in, what should the remainder be if it's actually a factor? It should be 0. So what they would do in the ancients, if they're like, I wonder if x plus 2 is a factor, you know what they do? They just plug in -2. And if it came out 0, they're like, it's worth it, I'll divide. What if they didn't get 0? Don't divide. Why would you waste the time? Because you know it didn't work. You follow me? So was this a little bit easier, or was this? I like the bottom better, don't you? Well, in fact, I'm going to even give you a better way to do that. So I've given you a couple little things today. First, what we're going to be trying to do is we're going to be trying to take problems that look like this, which are really hard to understand, and turn them into problems like that. But that means what you're needing to do is you're needing to divide them out into their corresponding parts. So what's your first thing to do is go, well, gee, what would be worth dividing? Well, if you look at it, what are the numbers that go into 3? 1 and 3. See that 5 right there? That's why 1 works and 3/5 works. There's actually a little remnant there. And so we're going to learn what are the possible things that we would even bother to try, so we don't go and just blindly start trying everything we could. Did you do that back in elementary school? You'd get your long division, you'd think first and go like, before I try something, let me think what seems reasonable. And then you'd go for it. You wouldn't just start writing down any number you wanted to. You'd think, oh, I think it's going to be 5, or I think it's going to be 6, and then you try it out. But you had an educated guess, right? We're going to learn what those educated guesses are so that we don't waste a tremendous amount of time, okay? So I did tell you there was going to be no homework over the weekend. I'm going to stick to that promise. Basically, we